Okay, differentiation by first principles. Let's go. We have a function f of x and its graph is here, and we have one general point with the coordinates x, comma f of x. We're not using y, and you'll see y in this example. And we have another general point here. So our goal is to find the gradient of this function at point x, f of x, right? That's what the differential does for you. So yeah, we have another point with the coordinates x plus h, f of x plus h. Now the distance between these 2 points in the x direction is h. The y direction, it's f of x plus h minus f of x, which you don't really need to write down. If we were to draw a tangent between both of these points, and let's do this properly. All right, good enough. If you were to draw this tangent, you would find that the gradient, which is delta y over delta x, this gradient is an approximation of the gradient of this function at this point x, f of x, this red point. So if we were to just simplify this, delta y over delta x, we would get f of x plus h from the y coordinate here, minus f of x over x plus h minus x, which can be simplified down to f of x plus h minus f of x over h. Now it's an approximation for our gradient. Now, you might be asking, how do we make this approximation any better than it already is? And to do that, we can obviously move this point, this blue point, closer to the red point. Let me make this a bit more clear. This blue point is going to be moved closer to the red point, meaning this distance h would get smaller. So if we were to do that, say the point is moved here, actually here, let's just go very close to the red point. The tangent between these 2 points would change a bit. Its gradient would be a bit more closer to the true gradient of this function at that red point. Yeah. So the idea is to move it as close as possible to x, the red point. Now, one question you might be asking is, what happens if we make h 0? Because, we want it to be as close as possible. So here's what happens. This is why we can't do that. If h is 0, m equals f of x plus 0, because h minus f of x over 0. And, just by looking at this, you can tell this isn't right, because we can't divide anything by 0. This would be 0 over 0, which is undefined. That's why we can't just substitute h equals 0. What we can instead do is we can represent this blue dot moving towards the red dot mathematically with a limit. It's called a limit. So we can say the limit as h tends towards 0 of f of x plus h minus f of x over h, which is our gradient, equals f dash of x, which is the differential for this function. So what we are doing basically is we're mathematically representing this blue dot moving towards the red dot, but it never actually meets the red dot, meaning h is never actually 0. It will keep moving more and more towards 0. So it go 0.1, 0.01, 0.001, and so on. So h would move towards that. And as we get closer, we'll get closer and closer to the red dot, meaning a better and better approximation of the gradient at that point. Now, we can obviously use this. Let's say we have a function f of x equals 2x. Now, if we use this formula, the one we just derived, we can say f of x equals 2x. F of x plus h would be 2 times x plus h, because this 2x is basically 2 times x, so 2 times whatever we put in. If we're putting in x plus h, it would be 2 times x plus h. So you can say f dash of x equals the limit as h moves towards 0 of f of x plus h, which is 2x plus h, minus 2 times x, which is f of x, over h. And we can simplify this further with some algebra. Remember to write the limit next to this until you get to the final part, because you may lose marks if you don't. So yeah, basic algebra. And if we cancel these two out, we are left with limit as h tends to 0 of 2h over h, which we can simplify to 2. So the final answer, so therefore, as h tends to 0, f of f dash x equals 2. So that's proving by first principles that the differential of 2x, of the function 2x, is 2. And if you know the power rule already, you can check it. So f of x equals 2x to the power of 1, f dash x with the power rule equals 1 times 2 times x to the power of 1 minus 1, which is 2 times 1, because x to the power of 0 is 1, which is 2. So it's correct. Now you can do this with any kind of function. So sine x, cosine x, but you might just need to learn the addition rules for them to like actually show it in the end. But yeah, that's differentiation by first principles.